Okay, starting with the diagram like this, we have find the measure of each angle. We can start by zooming in just on one vertex and say if two angles are vertical angles, such as these two, they have to be congruent or equal in measure, so that makes this angle 76. And we can also look at the diagram this way and say these two angles add to equal 180 because they're a linear pair. They're adjacent angles that form a straight line with their exterior sides, so we subtract 76 from 180 and we get 104 for that angle. And then vertical angles are equal, so those two angles are going to be both 104. Then we can look at the diagram a lot of different ways after that. We can, just getting rid of some of this that I just added to the diagram, looking at that given angle, we can say by one of our postulates that corresponding angles, and those two angles are corresponding because they're both above the two blue lines respectively, and they're to the right of the transversal, the red line. So therefore corresponding angles are congruent when we have parallel lines, and the arrows indicate that we have parallel lines, so therefore corresponding angles are congruent. Now we also have a theorem. If we didn't want to start there, we could say, for example, alternate interior angles are congruent. And see the Z-shaped figure? Anytime you have a Z-shaped figure, you have the inside corners of the Z, if the top and bottom are parallel lines, which they are. The inside corners are going to be congruent, so therefore if one of those angles is 76, the other one is 76. Or we could have stated that vertical angles are congruent, and therefore if one of those is 76, the other one is 76. So there's a few different ways. Then you could state that these two angles are supplementary, so you subtract and you get 104. Or from what we had on the screen earlier, if this angle is 104, these two angles are corresponding angles, and alternate interior angles are equal, so this angle and this angle are also alternate interior angles, or you have vertical angles are equal, or you have more supplementary angles. In any case, you can find all of the angles a number of different ways. You only have to know how to justify any one of those. Next problem. We're actually going to develop another theorem. It's not actually a proof. We're going to illustrate it with these particular numbers, but if you put in variables, it would actually be a proof. We want to find the measure of each angle. So in this case, I'm going to start right here, and I'm going to say here's a Z-shaped figure, so therefore alternate interior angles have to be equal, so this angle and this angle both have to be equal to 50. Now you could start a lot of different places. You could state, for example, this angle and this angle are corresponding angles because they're both to the left and above the two respective lines, so they have to be equal. Or now that we have the other 50, we can state that vertical angles are equal, and we get this angle. In any case, we can state vertical angles down at the bottom right are congruent, so if one's 50, the other one's 50. These two angles add to equal 180, so therefore the angle to the right of the 50 is equal to 130. And vertical angles down there are equal, so we have another 130-degree angle. And going over to the other vertex where the 64 is located, vertical angles are going to be equal, so if we have one 64, we have another 64. Adjacent angles that are supplementary right there. If one angle is 64, the other angle is equal to 116. Vertical angles are equal, so we have another 116. And we can look at the diagram a lot of different ways. We can say here's another Z-shaped figure, so the inside corners are equal, so if this corner is 64, this angle right here is 64. Then we can state vertical angles are equal, so we have another 64-degree angle. We can state the three angles at the top add to equal 180, so we add the first two angles together, 50 and 64, and we get 114. We subtract that from 180 and we get the missing angle at the top is equal to 66 degrees. So we fill that in and we fill in this angle right here as also being 66 because vertical angles are equal. What I want to focus in on right now is the triangle in the middle of the diagram. So looking at this triangle, I'm just going to draw it again down the bottom, and we will have a 50-degree angle, a 64-degree angle, and a 66-degree angle. And those angles, if we check over to the side, 66, 64, and 50, they add to equal exactly 180, which is the case for any triangle. The reason being, if we go back to this diagram and we get rid of some of the clutter, but if we look at the diagram this way, this angle, the red angle, and this green angle, and this blue angle, they add to equal 180 degrees. But this 64-degree angle is equal to this 64-degree angle because they are corresponding angles. Alternate interior angles that have to be equal. This angle over here would have been the corresponding angle to the one I'm looking at, or vertical to the other 64. And likewise, this 50-degree angle and the other green arced 50-degree angle, they are alternate interior angles, so they have to be equal. So because blue, red, and green at the top add to equal 180 because they form a straight line and they're adjacent to each other, blue, red, and green inside the triangle, this triangle, they have to add to equal 180 by making a few substitutions. So that's kind of an outline of the proof of the theorem that states for any triangle the angles add to equal 180. That's the interior angles of the triangle. Hope all of that helps. Good luck.